You are listening to Within Tolerance, a podcast for machinists by a machinist. I'm your host, Dylan Jackson of Proteum Machining, and this week I'm very happy to welcome Dave Arneson. Welcome, Dave.
Thanks, Dylan. Thanks for inviting me.
My pleasure. Both Cyrus and Phil were adamant that I had to get you on the podcast, and I totally agree because, once I had Cyrus on, I was like, oh man, PI sounds amazing. So before we get into your backstory, why don't you give us the backstory of PI? What is PI? What do you guys do? And how did you get into the industry?
Well, my dad and my uncle started it back in the late 1940s and 1946 or 1947. Nobody's really sure of the date, but he wanted to get into manufacturing. My grandfather was an optometrist who invented a eye training system called the Corrector, spelled with a K. And that was licensed to, I think, Bosch and Lomb during the Depression. And then after the war, he decided to my dad tried to start it back up again. That didn't really work so well on the corrector side. And he and my uncle started getting jobs. I think at one point he bought a hair drying company, manufacturing hair dryers with
Okay.
spun aluminum bonnets on them. And that didn't go very well because he didn't understand what people wanted, and they were switching at that time to molded plastic bonnets. But the molded plastic bonnets were expensive to get into, and he figured, well, the aluminum bonnets did just as good a job drying your hair. So that didn't go very well. I think an awful lot of the bonnets, I think a lot of the hair dryers ended up in, I think, Caracas and in Thailand, were a couple sales that they made. And gradually, through business connections and other things, he started doing work for Honeywell, amongst other people. But he and Al Sanner, our general manager, sort of credited the company getting into higher and higher precision through the buyer the buyer, I guess, would show up in a station wagon with a bunch of parts and drop them off. And as they were able to do more and more difficult projects, they got more and more difficult work. So they ended up getting involved in a bunch of cool things. One of them was spherical electrostatic gyros for submarines, for Honeywell.
Cool.
So in order for a spherical electrostatically levitated, however that works, gyro to work and allow a submarine to be underwater for, I don't know, weeks at a time, you couldn't do it with a mechanical gyro. But an electrostatic gyro with a period, I think the period in any direction of the electrostatic gyro was something like 120 seconds, maybe. I could be wrong on that. But making a hollow sphere out of, and I can't remember what material it was. It might have been molybdenum. But imagine making a hollow sphere and then grinding it and lapping it so that the period. My uncle has a patent, if anybody wants to look it up, on a sphere balancer.
Really?
That he made.
Wow.
An early patent of Professional Instruments was this balancer for spheres. And one of the ways that they did it is they'd make the sphere, they'd hollow it out in a lathe with a crazy little tool, and then there was a cap that would go on it. And I don't know, I suppose maybe the cap was welded on or it was attached somehow. And then you have this sphere that you're lapping. But in order to change the balance, you would like sand a little spot on it, and that would move the center of gravity over it. But you needed to know where to do the lapping of the sphere, or not, the burnishing of the sphere, in order to move it over the correct amount.
Oh my goodness. How cool.
That got us a lot of attention because, at least according to one person who was working at, that I talked to years later, that changed the whole defense strategy of the United States, apparently, being able to make these perfectly balanced spheres to go in the gyros, to not necessarily having to have bombers um, available to bomb Russia. You
Right.
could you could leave submarines underwater for, I don't know, maybe even months at a time,
Oh
and
yeah.
have them know where they were without surfacing.
Right. I was just watching a video a reporter did on the terrifying power of submarines, how they're this kind of unknown and untalked about branch of the military that, the silent service is what they kind of brand themselves as.
Yeah,
But the fact that, yeah, the humans are the limiting factor there. Like the power plant will run forever, basically, or at least long after humans starve. It's
but you
truly
don't know where you
insane.
are. You don't know where you are without good gyros.
Right. Yeah.
So, and that required better and better spindles. So to to do the turning, and the lapping is sort of a self-generating process. But that and other projects that we got into they got into were requiring better and better spindles. And my uncle went off, and I don't know if he was the person who invented checking spindles with a sphere to look at it instead of just checking the run out of the end of the spindle, which isn't exactly the same as the error motion of the spindle. Um, they were able to determine that just buying a more expensive spindle didn't get you a more accurate spindle. One of the more accurate spindles in our shop apparently was on an Atlas lathe, which was a relatively inexpensive, like step up from a hobby lathe.
Right.
And I remember when I started out here, there were Atlas lathes all over the place with various setups on them to do rather complicated things in a kind of a crappy old lathe.
Well, so this might be a good time then to preface the rest of the story. What are you guys known for now? When I had never even really heard of PI until Cyrus came on. And then after hearing about it, I kind of went on the little deep dive of your products and all that. But, if people are wondering what PI does, what are you guys known for?
Well, we're known for making, I guess, the most accurate spindles in the world. We sold the first micro-inch level spindle in about 1962. It was a dual hemisphere spindle that went to Oak Ridge Laboratories
Wow.
in 1962. And at that time, they had been investing in better and better indicators for it, and sort of fell upon the Johansson microcators. And in the early 1960s, I'm not sure when the first one was bought, we had a half a micro-inch per graduation. Um, and for those of you thinking metric, that's 12 and a half nanometer
Jeez.
contact indicator in the 1960s. So that helped us, really start understanding, or help my dad and Harold really start getting interested in spindles. And that spindle, the dual hemisphere, has some problems with load capacity and stiffness that that and my dad wanted a shorter spindle. So that spindle was, I don't know, a foot or foot and a half long, and wouldn't really fit into the machines that we had. And we wanted to be able to grind in machines, so you had to shoehorn this big spindle in that was rather difficult to manufacture. And my dad tasked my uncle with, making it a heck of a lot shorter. So our blockhead spindles are really kind of a triumph of getting the ultimate in accuracy out of a compact spindle. And we started making the blockhead spindles in the late 1960s, I think around 1968, 1969. And I was recently looking up some of that history. Some of the early ones went to Polaroid, and then a company called Fresnel Optics in Rochester, New York. And they were building their own diamond turning and diamond fly cutting lathes back in the 1960s. And around, I'm not sure, somewhere in that, my dad struck up a friendship with Dick Moore at Moore Tool. And one of the really early things that got us a lot of attention is on their aspheric generator, which is basically the first diamond turning lathe. They started putting our spindles in as the work spindle on those.
Oh, wow.
Which was a big deal, because Moore built everything themselves, down to the handles on the machines. They were very vertically integrated.
Right. So going back to your story, you said that you guys were making Honeywell parts and then needed, more precise spindles. Where did the idea of using an air bearing spindle or any of these precision spindles come from? Was it,
Well, air bearings were a big deal back then in the 1950s and 60s. There was a lot of research going on at laboratories around the world, trying to design and build air bearing spindles. It was kind of, I don't know, the hexapod or the 3D printing of the age. Lots of people were very interested in making air bearing spindles. One of the first commercial air bearing spindles that anybody would have in a shop was for tool and cutter grinders, for holding it was a rotating translating spindle that you could have like a little follower on it, and you could sharpen end mills on it.
oh, gotcha. Okay.
One of our early customers for air bearings was making a rotating translating spindle for Boeing. And interestingly enough, when my uncle Harold invented the step air bearing, he sort of didn't realize it, but Boeing had also invented the step bearing.
Oh, no.
And so they had to scramble around and get a license agreement. I think Boeing's patent was like maybe a month earlier than my
Oh,
Uncle Harold's patent. And then he decided, well, you could have a step bearing is kind of like what you see on an air hockey puck.
Mhm.
So it's got an area inside to distribute the air. Because if you think about it, if you just put a shaft into a hole, right? Just put a shaft into a hole, and it's a nice straight shaft and a nice straight hole. It won't float. It'll just shove the shaft up to the side. So you need a way to distribute the air around it. And you need some sort of a restriction at the end of it, which would be like the raised area on a air hockey puck.
Okay. Makes sense.
Actually, my uncle, his inspiration for that is when you hone a hole, and back in those days, a hone was the best way to get a nice hole. But if you're honing a hole, a lot of times you're either going to end up with a barrel shaped, which wouldn't be very good for an air bearing, but you could also end up, depending on how you hone, with a bell shape. And he had a shaft in a hole and he wanted to clean it out, so he put air in the middle and it floated. And he thought, wow, this is very interesting. He wasn't expecting it to float. He was expecting it to just blow the crap out of the hole.
Right.
And then he started working on step bearings. And the first blockhead air bearings, well, actually the first hemisphere bearings were also a step compensated hemisphere, which if you think about it, putting an accurate step that's about 200 or 300 microinches high in something that you're lapping is kind of a difficult process.
Yeah.
So
it sure sounds like it. So you were saying you guys made the air bearings for Moore.
Yep.
Is that when the company kind of transitioned away from Honeywell work, or when was that kind of break? When did that happen?
It was a long transition. In that we were still a job shop doing a lot of job shop work, although we probably didn't make the effort. It's kind of a different area of manufacturing to make to make things down on the 10 millionths level versus what you can do with a machine tool, like a lathe or a mill. And so we never really made the transition to being a job shop. We started back then into being but there weren't too many places to sell air bearings in where you could sell them over and over into a machine tool. Machine tool companies were very hesitant to sign up with us and make spindles for machine tools other than a few places. So we were in making copier rolls and other things that needed to be more precise. But it was sort of a gradual transition to where we are now, where we're predominantly an air bearing spindle manufacturer from being a job shop, and just realizing that you sort of have to concentrate on that. We made
Right.
some forays into making our own machine tools, which were semi-disastrous because we weren't really able to make the whole machine tools. And I don't know, probably around late 90s, we ended up becoming more and more just concentrating on being a spindle manufacturer. It's kind of an interesting industry because you need to have people that are looking for results down on the 10 millionths or lower level, which is, in the early 1980s, we were maybe the only people making an air bearing spindle that would make computer disks, diamond turn the computer disks.
Oh, wow.
And also the spacers, and also the machines to write tracks on computer disks and things. Although then a bunch of other people sprung up and realized that they could make a lot cheaper spindle. We were sort of locked into the blockhead design, which is accuracy and performance like the best you could possibly get. Interestingly, a spindle from 1969 is basically in our blockhead line of spindles is basically the same spindle as we're building today.
Oh, wow.
So that got us into a lot on retrofitting machines in our own shop, trying to make the spindles in bigger quantities. In the first big wave of disk drive work that we did in the 80s, we were trying to build these, machine tool, like things that you'd use in a shop, but they were way too expensive, and the disk industry didn't really need them.
Right.
Then in about 2000, we started getting back into the business of making disk drive spindles because the track density has went down, maybe from, I don't know, 50,000 tracks per inch or below, to when they started being a thing that you'd put into your hard drive at home, they were getting up to, quite a bit higher than that. And I think right now they're at about the individual tracks. The last time I checked, the individual tracks are about 2 microinches or 50 nanometers apart.
Jeez.
On that. So you can imagine trying to write these tracks where the spacing between the tracks has to be that. And we got a big job in around 2000 for making track writers for a company, and got into a thing where instead of maybe 100 or 200 spindles a year, we had to build maybe 2,000 spindles a year.
Oh, wow. Yeah, that's significant.
And our chief engineer, we tasked him to come up with a new design for a spindle that could be, sort of more mass produced. And then around the same time, around 2000, we started selling more into diamond turning machines.
I was going to ask, with the, camera lenses getting smaller and all of that, and, phones, and we've got all these things. Are you guys seeing, a pretty steady increase with all of that? Because I would imagine that a lot of that is, starting to spur
Yeah,
diamond turning lathes and all that.
we sell about 80 or 90 spindles a year into the diamond turning business, maybe a few more than that. But the tolerances are crazy. Our error motions on the spindle we call the 5.5 spindle are on the order of, the cutoff is 12.5 nanometers axial and radial error motion
Oh my goodness.
on the spindle. Yeah. And around that time, we ran into this. We had been going to ASPE, which is American Society of Precision Engineering. We'd been going to them, and there was a lot of talk about making more and more accurate spindles. So we formed a collaboration with Professor Eric Marsh at Penn State and started looking into how to, people before that, you'd measure one spindle down to that level. But when you're having to do 80 or 90 a year, the error motion techniques were, and then people want to know if it's got that error motion at 500 RPM and also at 10,000 RPM.
Oh,
So,
jeez.
so we went in and did a very big thing on really going after error motions. Actually, if anybody is interested, Eric Marsh wrote a very good book on precision spindle metrology. Is the name of the book that went into a couple different printings.
I'll put that in the show notes for anybody
Yeah,
interested.
yeah. It's called Precision Spindle Metrology. It's a very good book for anybody that wants to take a deep look into how to measure spindle accuracy, which is not as easy as a person would think. We went through, I don't know, 12, a dozen different things, and usually what we'd find is when we made our spindle metrology tooling better, our spindles miraculously look better. Because it's very hard to separate out the error of the ball, because we can lap a ball that's round on the equator to maybe 5 nanometers, but when your spindle has to be 12.5 nanometers or better,
Right. It's nearly half the error
it's
right there.
nearly half the error. So he came up with a rather clever way of using a way to separate out the errors that we're continuing to use today. But I got
That's
involved in the company when I was about 15 years old, which would be maybe 1977, working in the office as a 15-year-old doing the time studies, which actually worked out fairly well for me because I got used to doing spreadsheets by hand and having to have have everything add up correctly, because there were 50 guys out in the shop who were worried about their time down to 100th of an hour.
Oh,
So
wow.
I knew,
So did
yeah,
you kind of always know that you were going to go into the family business, or
not
did
not really.
Okay.
No, I wasn't. I wasn't a particularly good student. I wasn't really sure what I was going to do, but the job was always available. And back in the late 70s, early 80s, you couldn't just go out and find a job at a McDonald's or something. I remember applying for a job at Froggy's Pizza and never getting called back. so, started when I turned 18, started working out in the shop, and got kind of pushed off into the grinding area, and we were still still trying to be a machine shop. Didn't really do all that much in the lathes and mills, but started getting handed these crazy jobs for for different companies that would come in, and we had sort of a ethos that we'd never turn down a job because it was too hard. And that got us into some ridiculously hard grinding jobs, trying to
I
grind
bet.
these. One of the shafts that I was tasked to grind was I don't know, it was a 6-inch diameter shaft, 30 inches long, where the shaft had to be perfectly cylindrical, and then it needed a couple of thrust bearings on it. It was for a big oil hydrostatic spindle, and those needed to be perfectly square to the shaft. And
Oh boy.
and just sort of got handed this job after a while of putting it together. And I have, I think, some natural talents of of being able to figure out why, the shaft wasn't round or the shaft wasn't straight, and started doing more and more of that. It was a very crazy time at our company because we were taking on all these different tasks. I mean, all these different crazy jobs. NASA sent us one of our big jobs was doing the alignment optics for the Hubble Space Telescope, which at one time we had, I don't know, a dozen people from PerkinElmer just in working on our working in our shop, designing and building this crazy apparatus for allowing people to align up optics in space with giant gloves on, down to
How
a
cool.
crazy level. So I mean, the company was running all over the place, um, trying to do these crazy tasks that our engineers would bring in, and and you know, so we had at that time, I think, 4 different shops that we were working out of, and I went over to the grinding shop, which was away from the engineering department, but we just get these crazy jobs in, and just sort of flail around. I'd just sort of flail around trying to figure out how to make them, talk to people that were more experienced in grinding, and and try to figure out how to make stuff that these were the one shaft that I was working on that was particularly difficult was from Cranfield University for a big diamond turning drum lathe, and I'm sitting around trying to figure out how to make the whole thing on an old Brown and Sharp #2 cylindrical grinder, which really wasn't designed to do anything like that.
Oh
Um,
wow. So
and
what did your training look like? Because obviously they didn't just, take you from doing spreadsheets to and throwing you on the grinder and say, grind a perfect shaft. So what
well,
did
it
your training look like?
Well, it gradually got to that. I went to one shop and wasn't really getting along with the supervisor, and they sent me over to another shop, and the supervisor there um, was much easier to work with. But at least in my memory, I'd get these jobs and be tasked with going out and figuring out how to do them as a 20-something-year-old,
Oh
as
boy.
a 20-something-year-old, and the engineering department was over at the other shop. But they'd mostly just sort of leave me alone. I also got tasked with uh, putting the motors and encoders on spindles that we'd get, but they'd all be like a new design from the ground up, you know, based on just making the most perfect spindle design. So I didn't have a lot of supervision. I could just sort of go in and work on them. And I realized at that time that a lot of our problems were the tooling. And so kind of came up with a philosophy that I'd go in and look at a job and start working on trying to figure out how to retrofit machines, um, with better and better tooling. Um, when this job for track writing hit, where we had to build hundreds and then thousands of spindles a year, um, I got more involved and started thinking about, how could we do this? It was mostly manual grinders. So you're having people just, and grinding is an awful lot about repeating your process. And I started working with Mitsui. I had bought a Miltronics mill upgrade for Bridgeport, and
Okay.
realized, okay, I don't actually have to know all about G coding. If I could talk a grinder company into making me a user interface that did all that in the background, I could maybe, instead of sitting around and cranking the wheel to get just the right dress on it, and cranking back and forth to get repeatable grinds, because in grinding these parts were mostly um, aluminum oxide, or aluminum hard coat, aluminum anodized. It's a thick anodized, but it's basically a ceramic that you're grinding.
Right.
And so the amount of passes you take across the part, and the down feeds that you do, and how sharp your diamond wheel is when you're doing that. And fortunately, I ran into a salesman at Mitsui, and Mitsui was coming out with their first PC-based, relatively inexpensive surface grinder, and I talked them into writing me a easy programming interface for that, for rotor grinding.
Awesome.
and
How cool.
and and that was a big lesson for me, because suddenly, all the stuff about trying to remember just how much to feed down. If you overfeed a wheel when you're grinding ceramic, especially, the dress changes. The dress on the wheel, the dress condition just change. And um, was able to, with the help of them and their user interface, I was able to take parts that were very tricky to grind and make them relatively. I mean, this was the thrust surface on the rotor grinding on that spindle it has an 1.25 inch hole in it, and then the outside diameter is like 5.5 inches, and you have to get that whole surface flat to within a 10 millionths of an inch window.
Oh,
So
jeez.
so it's really important to have a consistent grinding process each time. So on those parts, we'll dress the wheel, grind the part, maybe dress the wheel during the grind, and then on the next part, dress the wheel before you start, and have one dress in between. And getting that consistent made the parts a heck of a lot more consistent. And grinding is a process where your process is very important, probably more important than even milling. Although I'm sure people that are milling parts run into the same sorts of problems.
Right. Well,
But
I mean, I'd argue on the global scale or the big picture, that's kind of machining in general. Like consistency
yeah,
is key over anything. You can make a terrible machine repeat if you're, approaching from the right
yeah.
end and all that stuff. So,
And that
yeah.
was a good thing for me, because I was trying to do stuff on machines where the tooling wasn't very well designed, and there was always this sort of theory inside the shop that if the tooling did the part once, it was good enough. Why are you Why are you remaking the tooling? And
Oh boy.
I remember going in and sort of having to not really even tell anybody that I was making a new stand for the air bearing to go into the spindle, because the previous stand was pretty wimpy. We make a little tilt base for grinding so that you can adjust the tilt of the bearing, and then you'll grind either convex or concave or flat just by adjusting a screw. It's basically a base with a flexure in the back and a screw in the front. Well, if you have one of those that's just sort of not thick enough or not heavy duty enough, it makes it harder to get uh, parts. And I realized that was really holding the company back, is tooling that was not particularly stiff or repeatable. And yes, you could get a good part if your dress was just perfect on the part. Dress on the wheel was just perfect, but as you ground, your flatnesses would change because of that. And started just going in and working with people in the shop and making better and better tooling around the shop. And I think that's one of the things where I've had the biggest effect in the company is just going out and throwing away the old tooling that was supposedly good enough and building new tooling. I was going to go around, and other than the fact that we had a power outage this morning, and I was
Ugh.
racing around that, I was going to go out and count the number of spindles in our main shop. We also learned to consolidate. We're down to 2 shops instead of working out of 4 or 5 different shops. And uh, but
Well, so you were
get
talking about experiences and learning. Confounded Machine asked, he wanted to know what experience or understanding has had the largest impact on your machining career.
I mean, just I suppose just trying to do jobs. One of the jobs that I had was a 20 some inch silicon carbide rod that needed to be ground cylindrical to, I don't know, maybe 20 millionths of an inch or so. And I was I was doing it in a Landis grinder that was built in in during World War II, and trying to figure out all the different things that I could do. I mean, I was taking techniques that had been done before on other shafts that were similar, but silicon carbide's a particularly hard thing to do. I actually made tooling so we could dress the wheel outside the machine, and realized that I had to dress the wheel once per part to get it to get that whole thing straight along the whole length to grind the silicon carbide rod.
Oh
Um,
boy.
and that was a job. I was just, okay, we've got this rod, Dave. You're gonna figure out. You're gonna be tasked with grinding these rods and trying to figure out how to do it. So basically, it was, I'd say, getting harder and harder jobs to do, similar, I suppose, to my dad and my uncle in the 50s, although I had the advantage of having blockhead air bearings that I could put in and do it.
Right.
I didn't have to invent a way to make an almost perfect air bearing spindle design. Uh,
What have you learned then, maybe about how to characterize a job? Because I imagine, a lot of us who listen, are working in aluminum. Like I can throw away a piece if I screw something up. But my guess is that a giant shaft like that, you have found ways to approach something that you cannot scrap and really make sure that it works the first time.
yeah, in that case, patience, especially on the first ones, is patience is key. Grinding a shaft that, I suppose, the first ones, those silicon carbide rods, that probably took me a couple weeks or more to grind one shaft. and learning that if you get impatient, and that's one of the things that the CNC grinders have really helped with, because you program that in to take 50 millionths down feeds or even 20 millionths down feeds. You're not standing in front of it cranking the handle back and forth
Right. Yeah.
for for uh, for what seems like an eternity, um, to get a part. But if you're doing that and you overfeed, by getting impatient, you can add a lot of time to it. And I think I've learned, how to ask questions of people, talk to the people doing the job or who have done a similar job, asking them for their experience, and hopefully making sure that people don't think that I'm appropriating their ideas, so that I can ask them again a next
Right.
time.
So,
Uh,
what would your process for that? Like, are you taking a depth of cut and then characterizing what that cut looks like, in terms of straightness and flatness and all of that, and then extrapolating from there? Or, how do you approach even something like that? Like, I feel like on jobs like that, I constantly would be worried about, oh, well, it acted like this up here, but then when I get down to final, it's going to go out of whack. So, like, how are you making sure that you're characterizing what the final part's going to look like early on?
well, we have in-processing gauging that was developed before I started working on it, that will allow you to see, like on a shaft like that, you'll grind and then you'll measure along the shaft, see that you're getting what shape the shaft is. We found something kind of interesting on that job, is that the the grinder, the way it was set up and working, tended to grind a shaft that was, let's see, was it bell mouth? I think it was barrel shaped. So we actually raised and lowered I'm not sure who thought of it, but we lowered one center on the workhead side quite a bit, and the other one on the wheelheads, or on the tailstock side, we raised it so that it would grind a straighter shaft by doing that. I mean, one of the things that Professional Instruments has always had is an idea that there's probably a way to fix the part through fixturing and cheat a little bit extra accuracy out of a part by doing something that you weren't necessarily thinking of doing before. But yeah, for me, it's basically, the idea that you can make the process work. You can get down to those levels, and making a mistake isn't necessarily the end of the world if you learn from that last mistake. And then also, at one point we had it in our heads that, we'll have things that have proven to be true, and then, re-looking at it. We had a long-term employee that started in 1962, and he was always a good guy to go to and bounce ideas off, and maybe appropriate some of his ideas into, and try to make it work for myself. When I'd get these difficult jobs, I'd go out to lunch with Mel and talk it over, and go off and try something else. I was never told specifically that I couldn't go off and try something different. So I'm not sure that the way that I was trained up would work off in the future, but it definitely worked for me to be handed these seemingly more and more difficult jobs and then run them.
Yeah, it sounds like
So,
it. Another
so
question we got from the Patreon, Josh Hacko, last week's guest. He said, seeing all the videos that you post on YouTube is fascinating. And he sees all these different brands of machine tools that you guys buy, specifically surface grinders. Why do you choose one brand over another during your purchasing process?
well, the Mitsuis we chose because I had been going around to tool shows and talking to different grinder manufacturers and salesmen, and Mitsui was the only one that would sell me a machine with an interface on it that I could use for rotor grinding. In rotor grinding, you're setting a spindle on top of a surface grinder, and convincing them that I wanted a CNC grinder that would do that. That relatively simple process, and in a way that somebody that doesn't know how to G code, because I don't know how to program a machine in G code would do it. And most people that spend their careers grinding in shops or an awful lot of them are using older equipment. So when they told me that they'd make one, I bought one and started working with them, and we now have 11 of the Mitsui surface grinders. Later on, I wanted to have a CNC grinder with an easy to use interface, and I went to Parker, and Parker made me some. They modified their program for cylindrical grinders so that we could use them for what we do. And so I bought theirs. So an awful lot of it has to do with being able to work with their people that will do the easy programming. Because when we're hiring people, we're not necessarily trying to hire people with machine shop experience, because most machine shops aren't working to 10 million tolerances. So
Right.
you have
Yeah.
to sort of start from that, and it's almost an impediment to understand how to work to tense tolerances to go into the grinding. And so I really wanted to be able to have machines that were relatively quick to being up to the point where people could make good parts. Yeah, so Parker made me an easy to program thing, so I bought theirs. I bought an Okamoto CNC cylindrical. Although in that case, their programming worked reasonably well with the way we do it. We'll buy a whole CNC cylindrical and just use the CNC part to set up the end stops on the grind, and then feed in by hand. Now you'd be surprised, but most CNC grinder companies don't make a grinder that you can just feed in, or at least at the time, didn't make a grinder where you could feed in by hand. But in our grinding, especially if you're grinding a big long shaft, being able to feed in by hand and have it go back and forth and dress the wheel, it doesn't seem like a big problem until you're faced with the fact that your parts are all different sizes when you start in grinding. So if you set up a CNC program that for your biggest part, your next part might be grinding error for, if you're feeding in 50 millionths at a time, your next part might be grinding a part and have a half an hour before it before it actually starts touching the part.
Oh boy. Well, so you mentioned training people. Brings up a great question. Level Up CNC asked, with the limited supply of skilled machinists in the future, how do you ensure new employees get trained enough to work on with supercritical tolerances like you guys do?
Well, we have a lot of equipment for checking the parts. People out in the shop will grind a part and check a part, and so they get instant feedback. We're not generally sending the parts off to an inspection area to check. So and with the CNC grinding, and we'll generally have a person set up on two grinders, so they're loading one part in one machine, and then they're flipping it over and grinding the second side in the second machine. We have roundness testers. I think we have 22 roundness testers that can be used for checking circular flatness on the part, which is usually the biggest problem when you're grinding. Like some of the parts that we're grinding for one company are maybe quarter of an inch thick and 6 inches in diameter, and you have to get it flat. And
Oh boy.
so you're flipping the parts a few times to grind, but having that roundness tester that gives you that separates out the out of parallelism of the part, because it's going down onto a fixture on the roundness tester that's been ground in assembly. So the top of the roundness tester is running perfectly true. So you can set that down and you can see, okay, my part's potato chipped. It's got a big two lobe in it. Um, I'm going to have to get that out, and I have to get that two lobe out before I take it down to the size tolerance. But you can see that on the screen before, when you're just looking at it with an indicator, and the indicator is moving up and down and doing a couple little wags in it. It's really hard to separate out the out of parallelism from the out of flatness when you're just looking at it like that. And
Totally. Yeah.
and and that was a big part of it, is that's much more accessible. You see the polar chart on the roundness tester, and it looks like an egg. And okay, well, that's a two lobe. I'm gonna have to do something about that when I'm grinding. So we're basically hiring people. I mean, we've hired people out of a lot of different industries, and or like people that work in food service or retail that have reasonably good mechanical skills. We have a mechanical skill test that we give out to people to get an idea of whether they, know know inherently, if a train is going around a corner, which way will it fall over? things things like things
Okay.
like that.
So, what are the first, few weeks or month of a new trainee's day look like? Are they shadowing somebody? Are they working, you know, hand in hand just to do the inspection so they kind of understand the tolerances? What are the first steps when training somebody like that?
Well, an awful lot of times we have one cell of grinders where we have three Mitsuis, and so we'll just put them in with an experienced person once they get into the grinder. Maybe they're bead blasting parts first, or helicoiling parts, or things like that for a little while, and then if they look like they're going to stick around, which is a good reason to hire people out of working in a pizza shop, for instance, uh, uh, because they're maybe more inclined to learn how to do this work, because it'll pay a lot better than a pizza shop,
Right.
or retail, and see that they know what they're doing. Maybe work on deburring or bead blasting for a while, um, and then put them in with an experienced person in this new cell that we have, and have that person grinding parts while they're on two machines, while they're grinding parts on one machine. We have a big job for making lens holders for a company where the tolerances on the flatnesses are about what you need on an air bearing, and and so we'll basically, it's still a bit of throwing people into a situation and seeing what they can do. It's a little bit different than, well, I suppose it would be similar in a job shop running CNC machines, uh, to being a machine operator, to then learning how to program or make offsets
Hmm.
and things.
Okay.
So it's basically learning by experience. But again, there's not a lot of outside training that you're going to get, like going to a trade school, that would be valuable, that you that they'd learn something in a trade school that would be valuable to working here, because those people are teaching how to machine parts, and we don't do a lot of machining in house. We have a Haas SL30 and a Haas VF3 where we're making some of the parts for air bearings that are kind of critical. But the guys up there are pretty experienced, and we're not really looking to expand that. That's more um, for that. But yeah, I wouldn't say we have an exact training things, and then jobs will open up as people retire, more and more difficult. we have a whole range of grinding, from things that we can get people up and working on in a couple of weeks to things that are probably a few years before they could handle those jobs, and and sometimes they're maybe never going to get up to the point of some of the fussier jobs, like grinding an air bearing shaft for one of our 5.5s, where the shaft has to be absolutely perfect, otherwise we'll see error motions in the spindle. That job isn't a training job. That's a job for somebody who's much more experienced. But those people retire, or or they get sick of that job. So we have people of all different levels out there. We just hired a new guy who was working in a pizza shop, and I think right now he's probably going to be doing helicoils on aluminum parts or things like that for a few weeks while we decide whether he really wants to work here for a while. Machine
Right.
shops aren't as exciting. You watch some of these shows on YouTube, and they make it look like machine shops are super exciting. They're not always super exciting.
Right.
And
Right. Yeah. Well,
and
I mean, I think every job has its monotony from time to time.
yeah,
Everybody, you can't be always excited about everything. That's just not how life works. So,
yeah. And if you're often we'll get people in, and they'll say, "Oh, I'm super excited to be working in a machine shop," and they're gone a week later.
right. Oh, yeah.
uh,
Yeah. Let's see. So we had a couple questions about the tidbits. So JT at
okay,
DFM asked, on one of the 50 tidbits, you guys say ground surfaces go together better than lap surfaces. Can you explain that?
sure. I mean, you think about it, ringing together a pair of gauge blocks, if you're familiar with that. Um, you can't really there. You don't necessarily, if you have something that's precise, that you want to have it ring in. Let's say you have a fairly thin wall part that you lap the surfaces. Those would ring in, and then when you're trying to assemble it and dial it in, if it's rung together, you can bend a steel shaft that's fairly thick, um, just by tapping on it if you have your screws too tight. Well, in a ground surface, you don't have anywhere near that many contact areas. It's similar to a scrape surface on the top of your or a flake surface on top of your mill. I mean, that's a better surface to put together. You don't really want things ringing together in a
That makes
precision
sense.
assembly.
Yeah,
So
that totally
you
makes sense.
so you have a bunch of little points. You have sort of a structured surface that's going together that won't tend to ring together as much as, well, if you looked at a surface plate, for instance, a granite surface plate, there's a lot of area in there for, if a granite surface plate didn't have a lot of, if it had too much contact area, you wouldn't want to make a lapped steel or a lapped granite surface plate, because if you set your parts down to it, it might stick to it.
Right.
You might
That
need
stick
you might
forever.
need
Yeah.
to you might need to take a hammer to it to get it to. You might need to take a hammer to get it apart. It's a great surface for ringing together gauge blocks, but not everything can go together sliding it on. You try
Right.
to put two gauge blocks together end to end without sliding them. There's an awful lot of places where you can't do that.
That makes sense. Definitely. Our other one was from Cyrus. He says, first, thank you again for letting him work there.
Hmm.
And second, he said, what is the most important tidbit?
I was looking at that on the tidbit list, and I highlighted a few of them. I liked having worked with Invar. Uh, it's always struck me that in a shop that's doing things out of steel, Invar's coefficient of expansion is just as far away from steel as aluminum's coefficient of expansion.
Oh, wow.
So So you think about making a precision thing, you wouldn't want to make a precision assembly that had parts in it of different coefficients of expansion. So uh, that was one of the things that, for a while people were wanting to make everything out of Invar because it wouldn't expand. But you're probably gonna end up bolting it to something made out of cast iron or maybe even aluminum.
Right.
And then you're twice as far away. Your precision assembly is going to even be more of a thermometer than that. Another one that I was thinking of that took me a while to realize is that number 44, which is running your grinding wheel at a slower speed, sometimes gives you better parts. It's interesting. An awful lot of machines are made in places where they run 50 cycle per second or 50 cycle electricity.
Right.
So, and then they'll sell these machines in America where we run 60. So it's going at a different speed. Well, a lot of machine tools vibrate at that speed. So just turning it down or turning it up will get you past that natural frequency of your machine.
Interesting. Yeah, it's, as somebody who doesn't work down to that level of precision, I've never thought of, oh, my machine might be micro vibrating because of the electricity. That's
Well,
really interesting.
yeah, Tony Schmidt's. Well, it's the speed of the wheel. The wheel is sitting there putting out. Even if you have it perfectly balanced, it's wants to shake at 60 hertz,
Right.
maybe, and maybe just slowing it down. I know Tony Schmidt's at University of Kentucky is now doing an awful lot of stuff with that on tap testing tool holders, doing a tap test to see what the natural frequency is going to be and then not running it at that natural frequency, not trying to do your milling at that natural frequency. So that was a tidbit that I thought was good. And then number 10, check to see if your indicator tip is loose. I can't count the number of times that I've walked up to somebody who's having a heck of a problem on measuring something and their indicator tip is just loose and it's giving them all sorts of trouble, and you tighten up the indicator tip and they work their way loose.
Oh yeah.
And then
we see it with probes too. You all of a sudden you start seeing this crazy probing error, and then you're like, oh, the tip's kind of loose. Okay.
and then don't necessarily believe your gauge that has the highest resolution. That's somebody sees something written out. I started putting on digital readouts on some of the grinders that had pretty coarse infeeds, but you'd feed in and you'd listen to it when it started touching and grinding. And I put in a digital readout on that grinder that read out in 10 millionths of an inch. And they started believing that and believing that they moved at 50 millionths, their part should have gotten 50 millionths smaller or something. Or, and if you've measured something with a really complicated setup to measure down to 10 millionths, it's not a bad idea to check it with a caliper to make sure you haven't missed your size by some enormous amount.
Right, a full rotation or something. Yeah.
A full rotation, your micrometer. That's a good one to have miss, or your indicator is stuck and your dial indicator is stuck or something like that, and you've gone a whole revolution past where you thought you were.
Oh yeah.
And then obviously everything is rubber when you measure in micro inches is a good one. So those are sort of my favorites from re-looking at it again after the question popped up.
Awesome. Let's see. Marvin asked, could you envision an aerostatic tool spindle with through spindle coolant?
We've done it. I mean, you basically just need a hole in it and you can hook up like a Dublin rotary union on the other side.
Okay.
We've made one of the projects fairly difficult project that we've made is a water-cooled spindle for a synchrotron, where they're shooting the beam. The beam is like 500 watts focused on like a pinpoint, but they want to use synchrotrons for lots of different experiments to make high power X-rays. And so we have a disc that spins inside of a vacuum, and it's water cooled. The disc is, it's not through the spindle coolant, but
Okay.
uh, uh, but it's cooling the disc, because otherwise the disc would melt after a little while, being in a vacuum, not having any way to dissipate the heat. Um, so you can do it. There's different ways, but an easy way is to just hook up like a Dublin. Dublin makes water rotary unions. They're ball bearing. It's a ball bearing rotary union, but it can be retrofit onto one. I'm not sure for what he's trying to do, because he's probably wanting to go 60,000 RPM or, or 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 something crazy. We've kind of we've kind of decided a while ago not to make um, tool changing high speed spindles for milling applications. There's a company in Germany that I think he's buying his spindles from right now, that makes a high speed tool changing air bearing spindle for milling applications. But in milling applications, you don't necessarily need repeatability on that, but you don't necessarily need super high accuracy on a rotational accuracy on a milling spindle. And it gets rather hard to make an air bearing spindle that'll go that fast, because air bearings, of course, are all about the area of the air bearing itself. You can make
Right.
an air bearing that holds a couple thousand pounds, but you need a lot of area on that. Then you start running it fast, and the shear in the air. I mean, air bearings aren't frictionless. There's a shear in there. Our 60,000 RPM spindle that we make for real fancy diamond grinding and really fancy diamond fly cutting, it develops, I don't know, several hundred watts of power just in the air film. That's
Oh,
60,000
wow.
RPM. So uh, uh, it's rather light duty compared to a spindle that would go into an actual machine tool, like a Kern or something like that.
Right.
And like I said, there's a guy in Germany who's doing seemingly a pretty good job of that. And then trying to figure out how to get a tool changer into an air bearing spindle that will take advantage of the accuracy of the spindle. Um, that gets rather difficult, because that tool changer has to have a shaft in it with maybe springs in it to hold it, and then you've got to have a lot of spring force that tends to bend the spindle around. And our clearances in our spindles are, the flying height is only, you know 250 300 microinch flying height. It doesn't take very much to bend that shaft around. So after a long time of trying to figure out how to do that, we just decided that we're going to strictly concentrate on real high accuracy spindles that aren't necessarily under a lot of load. And I think we've pretty much decided that 60,000 RPM is going to be the fastest spindle that we ever make anybody. It
Okay.
was it was a long learning curve. We're still we're still perfecting that spindle, 20 years after it was designed.
Right.
Uh,
uh, Kyle Brunner asked, "What's the most critical piece of equipment for your operations?" And I imagine today you might say a generator,
a
but
generator, yes.
outside of that,
Well,
what would
then
you
there's the
say?
then there's the air compressor. We have a 15-year-old screw compressor that we recently had a problem with, and we decided to just buy a new one, because at first, when we were diagnosing the problem, it was going to take months to get to get it repaired. Fortunately, we figured out how to buy a component on eBay and go in there, and our electrician guy figured out how to buy a component. So, I mean, obviously, the most critical thing that we have in the shop in general is our blockhead air bearing spindles that are on well over 50 machines in the shop are holding at least the part, and maybe even holding the grinder spindle, the wheel spindle on it. So we really couldn't do anything without a blockhead spindle. But in general, when we have a critical machine that's likely to break down, we buy an extra one, so we always have it available. But
Right.
but strictly speaking, I mean, we don't have a business model that doesn't involve doing things on air bearings.
Okay. So since you guys replace the spindles in a lot of these machines, what are you looking for? I mean, besides the programming interface, what other things are you looking for in a machine when you buy it? Because, obviously the spindle you can kind of discount.
Yeah, a way to put the spindle in. And when I bought the Parker cylindrical grinders, I bought Parker's partly because they had, especially on the wheel spindle, they basically just bolted the wheel spindle onto a slide with a T-slot track on it. So that was pretty easy to take their wheel spindle off and put our wheel spindle on it. So if I bought a Studer or something like that, retrofitting in an air bearing spindle for the wheel spindle would have been difficult. It's not as big a deal in a cylindrical grinder, but in an ID grinder, one of the problems with most ID grinders is they're depending on a taper for mounting the ID grinder spindle in, or mounting the ID grinder wheel in. And you might have a wheel that's sticking out, 8-10 inches from the front of that taper. Well, those tapers don't match perfectly, and that nut that holds it on doesn't hold that in there perfectly. And so our air bearing has a nice big flange on it that will, with a 3-inch bolt circle on it, that'll hold that wheel mount. So on some of our air bearings, we have like a foot long wheel sticking out from the face of the wheel spindle. So if you did that with a taper, you'd play heck trying to grind and remove, like 100 millionths of an inch on a pass, or 50 millionths inch on a pass, because it would just sort of push and push, and then it as soon as you get it all preloaded, then it'll grind in hard. So
Right.
taking light cuts in especially in an internal grinder with the taper mount is a big thing. You think about the way the taper goes on to a surface grinder wheel. Your wheel is kind of right over that taper. I mean, it's very close coupled to the taper mount.
Hmm.
and and the retrofitting the spindle out of that. We haven't on our new surface grinders that we've purchased in the last 20 years. We don't ever retrofit the wheel spindle with an air bearing. Some of the older spindles, ball bearing spindles have gotten a lot better in the last 70 years. So, so
Right.
a ball bearing spindle from the 1950s is nowhere near as good as a ball bearing spindle of today. So there's no real reason for that. But we generally like to buy spindles or machines that are open enough and easy enough to retrofit in the tooling that we're going to retrofit in.
Okay.
And in surface grinders, you usually have that anyway, because they're built 12 by 24 or 8 by 18. It's pretty easy to put in a spindle on the table of that.
Right.
Even almost anybody's machine will do that.
Makes
Yeah.
sense. So that brings us on to shop news and new things. Are there any new things you guys are coming out with? Any new projects or anything that's new and cool in your world?
Well, we're working on oil hydrostatic spindles. Um,
Oh, that is very cool.
and we have one that's basically the same size as our 4-inch blockhead um, that our engineer Danos designed many years ago, but now we're working on a 10-inch version of that. So a 10-inch blockhead, the radial load capacity in a horizontal application is about 200 pounds. Well, with an oil bearing, we can easily get 2,000 pounds of radial load capacity off of our oil bearing, and and then it's a nice compact oil bearing. A lot of oil bearing spindles are long, and so they don't necessarily retrofit into something that's small. So I have hopes to maybe get into some of the areas. Diamond turning, people aren't afraid of air bearing spindles, but like for a grinder for grinding hydraulic components or something like that, we've had very limited success selling those into companies. I think there's one company that grinds fuel injector valve seats for us, but they're about the size of a pencil eraser, and and so and they still crash them every once in a while, but they can grind rounder valve uh, seats in those, and they can get off their ball bearing spindles. But an oil bearing is going to be a lot more crash resistant and usable in a real machine shop. I've been looking over what we're selling into, and we're selling an awful lot into the semiconductor industry right now, and that's boom and bust. And also into the optics business, which is in the middle of a long continuous boom, but who knows how long that will last. So we have that project. I'm looking also into easier to program machines for, because we can get, if we're if we're buying 50 or 100 parts for air bearings and we have a long time to wait, we can get that done out in we have a couple of good subcontractors nearby who do the lion's share of our blanking in machine tools. But if we have to get 6 parts done in a hurry, we can't do it. We bought a track mill a few years ago and a track lathe. Track mill looks kind of like a Bridgeport mill, but they also make one that programs the same, that's a full CNC with a tool changer and an enclosure and Cat 40 tool changer. And so I'm looking, and my son Henry is very excited about getting one of those and trying it out. And we're still doing a lot of those parts that we're running in small quantities in a Bridgeport with a mill power, Accurate mill power on it.
Oh, gotcha.
Or we've got several of those. But then somebody's sitting there and having to run the handle up and down,
Hmm.
and so it's very easy to program in the machine, put in a bolt circle or something. But let's say you want to do 6 of them or something, it'd be awfully handy to be able to do it in a full CNC mill. And the track mill seems to have a very nice um, interface and operating system that you can, pull in a DXF file and easily pull out all the unnecessary stuff and get down to the things that you have to mill. So that's another thing that we're looking at. I'd I'd like to buy one of those and see how it works, and maybe even concentrate our sort of little flex shop or small run shop around the track lathe and the track mill.
Okay, that's great. Well, that brings me to the last question I ask every guest every week, which is, what did you research this week? It doesn't have to be machining related. It's just always interesting to see what interesting people are looking into. I've had people talk about what they can feed their babies, or bicycle parts, or computers, or whatever. But what's been popping up in your browser this week?
Let's see. I was thinking about that. Uh, uh, One of the things I've done is Minnesota Precision Machine Tool Manufacturers Association, MPMA, runs this kind of cool. It's almost like a user group of machine shop owners, um, and I've been researching that and thinking about it. They're more in line with the whole, like, how to run a whole machine shop. So I've been looking into I have homework for next week. I forgot to I forgot to grab that sheet, but more on how to how to deal with, we make 20 different basic air bearing spindle designs, and they're all different, and it's a logistical nightmare on how to make sure that the parts are coming in at the proper time to be able to ship things at the proper time. So I suppose it's more of just looking into what sort of tools are available to handle that, and also handle how to make it less of a job where people are just sort of running around and saying, "Oh crap, we forgot this. We forgot to make the sleeves on time, or we forgot to make uh, other things on time." So that's sort of been at the back of my brain for a
Okay.
while, trying
Inventory
to
management and things along those
inventory
lines.
management. We recently have been trying to implement an ERP system, but unfortunately, the ERP system isn't that great on that we have on parts that aren't really on order. When we're making an air bearing spindle, like a 4-inch blockhead air bearing spindle, we're starting those parts way before we get any orders.
Right.
So because they take a long time. I mean, just the coating getting the coating put on one of the pieces of the air bearing before we even touch it after the coating is, many month process.
Oh wow. Yeah. So it's not
And
something you can make to order because otherwise the lead times would be insane.
the lead times would be insane, and people want to be able to call us up and order an air bearing spindle and have us have it in inventory, or at least not have a 6-month wait for it.
Right.
And we're constantly getting caught on that. Each spindle has, some of the spindles have 50 parts in them that we have to make. Some of the spindles have 6 or 8 parts that we have to make. But trying to make that less of a crisis, because the shop runs a lot better when, we'll run 50 or 60 blockhead stators through the shop, and it's a lot easier if you don't have to, like, try to rush some of those through, because they'll get touched by a grinder. The stator will get touched by a grinder 6 or 8 times at different levels of the at different levels of the grinding, and if we have to start all from scratch. So yeah, and that's sort of what I've been thinking about, not necessarily researching, because the last year or two have been a slow moving fire drill around here.
Yeah,
Trying
that's
to trying
a
to stay
tough
on
thing.
top of trying to stay on top of things. And we used to use these things called inventory cards, but those, you only find out how many parts you have when it's at a certain set point. You don't
Right.
know how many parts that you've started and
Right.
have
Yeah.
in process, and the parts kind of work their way through almost on autopilot once you start them. So I'm trying to come up with a sort of a dumbed down version that can give me or somebody a overall view. If somebody comes in and says, "Well, I want 20 of these spindles. Can we actually even make them?"
Right. Yeah.
And
That's a really tough inventory management problem because it's not like, the normal thing of like you're machining it and it's pretty quick, and maybe it goes out to anodize or something. It's, like you said, many months. That's rough.
Well,
That's
and the
really
way
rough.
we look at it too is, to keep our people busy, we have to have things that we can pull out when our and when our lens holder job drops down. We have to be able to pull people off of making the lens holders and have some other job for them to work on. So it's a nice way, and it's better than putting money in the bank to have these parts in inventory. But um, we don't always have them. Always have them started at a time, and everything has been. We were ordering steel for our 5.5 spindles a while ago, and the delivery times went up by about triple. And
Oh yeah.
our machine shops that we deal with, our delivery times have gone up by about triple on those. So we have to we my new system that I'm working on with a programmer that I know, actually is my nephew, who's going to program this thing, will be able to hopefully tell me pretty quickly how many parts we have in process overall. Not necessarily how many parts, because I can figure that out just walking out into the shop, but I can't necessarily figure out that we've run, completely out of this or that part and start them in time.
Right, right, right.
A blockhead stator, I probably want to get down to like 20 or 30 of them in process before I start a new order of ordering steel to get them in. And I don't think that anybody makes an ERP system that works like that. At least the one that we have doesn't seem to be. It's more thinking about it when the order is put in place.
Right. Yeah, it's looking
And,
at finished goods and orders, not in process plus orders.
yeah, and it's not necessarily thinking that somebody's going to go out and order a whole bunch of stuff in advance, because that's sort of our business model. Is people can come in and buy a very special spindle and get it within a couple weeks, depending
Right.
on if it's just a bare spindle or something. So,
Oh boy. Yeah, that's rough. Well, I wish you the best of luck for
all
sure.
right,
ERP stuff is always, I feel like, a sticking point with a lot of people. So I definitely keep my fingers crossed that things work out with that
yeah,
ERP. And if not, that you guys find a solution that works.
yep, all right,
Well, thank you so much, Dave. I
yeah.
really
Thank you,
appreciate you
Dylan.
taking the time. I've learned a ton. Thanks to all the Patreon members who make the show possible. Thanks to Brett, Leaper Manufacturing, Cosmos, and Joe. Thanks for joining this month. Really appreciate it. Thank you all for listening, and I'll be back next week.